Good, good, great. So this lab is actually one of the easier labs. I think the first lab was harder than this lab. So hopefully that's good news for you guys. This is the half adder circuit. You should have seen this by now. You guys have any questions about the half adder before we continue into the full adder? Okay. The difference between the half adder and the full adder, as we will see, is that the half adder has only a carry out and not a carry in, which means that it can only add two 1-bit numbers. So basically a half adder would be like 2 to the 0, this column here. If we wanted to be able to move into the 2 to the 1's place, we need to be able to carry. And that's what the full adder gives us, is the ability to carry into another place. This is our truth table, which I will come back to because I want first to look at the block diagram. So this is what is called a, wait, hold on. I want to look at this block diagram, this circuit. Okay. So yeah, so pretty simple, straightforward. It's just like the half adder that you've seen before. It's got an exclusive OR for the X and Y, but now it also has an exclusive OR for the carry in, because your sum has to account for the potential for a carry as well. And then over here it's the carry out, and now we have an AND not just for X and Y, but for X and Y and X and C and Y and C. Because there's a possibility that we end up with 3 ones in a column because we're carrying it. We need to account for that as well. Questions about that? Great. So I'm going to come back up to here for a minute, and this is what the block diagram looks like. It has the carry in, it has X and Y, has the sum, and it has the output. Truth table, you can look at this on your time. I would take note of this and take note of this if you can, because those are the logic equations that you'll need to create your full adder. The first part of today's lab, we will be creating this circuit, and then we will be daisy chaining those together to create what is called a ripple carry adder. The ripple carry adder is so named because you have to connect them one after another in series, and the values just ripple through it. What ends up happening here is that each full adder represents one place value. So we have a full adder here for S0, a full adder here for S1, full adder here for so on. So each one of these full adders would correspond to one of these zeros or ones if we were going to do it manually. So full adder for each place value. The longest path through that is going to be from the first adder all the way to the last carryout. Because in order to compute our values, we have to go through the chain. For this reason, this is not a very popular design. There are more performant designs out there, fast adders and carry look-ahead adders, which we will be implementing next week after you've had a chance to learn about them a little bit more from Dr. Kalla. This is the simplest of the multi-bit adder architectures that we can create. Any questions about what we're doing? Any questions about the theory here? Excellent. So let's jump into the verilog. I'm just going to do it in VS Code for now. It's easier and faster. Minimize those. All right. So I've created 2 verilog files here to start with. I've got my adder.v file and my 4-bit adder. My adder.v file is going to be a single full bit adder. So just one of these guys. So in order to do that, let me make this a little bigger. Let's take a look at the inputs that it takes, and we'll go from there. So what's the very first thing that every verilog file needs? A module, right? And we should always name our module what? After the file name. So when you create a project, you'll always be given the first file as the project name. That should be your top level file. That should be the thing that goes on your board. If you're going to be creating, like we are, if you're going to be creating it in pieces and building it up like we are, then you'll want to create separate files for each of those component pieces. And they should always be named the same as the file name. So your module name and your file name should always be the same. That's not a strict requirement as far as the compiler is concerned, but it can cause some problems along the way if you don't with different tools. And it's just better practice to always have it that way. All right, so in this case, we're going to call this adder. And we need some ports. What ports do we need? Let's look. This is our full adder circuit right here. So can somebody kind of guide me through? I'm going to let you guys drive a little bit more this time around so that we make sure that you're understanding the verilog too. So can somebody help me with the inputs and outputs? What can I put in here to correspond to this sort of diagram here?
Just a 1-bit wire for X, Y, and Z.
Yep, okay. So let's go ahead and do those. Those are my inputs. So I'm going to put input wire X, input wire C, input wire Y. Okay? Now what about my outputs? Okay? And when I'm just 2 wires? Yep, that's right. So output wire S, output wire C out. And I'm going to go back and change this C to be a C in so it's a little more clear. Just where I put C, I'm going to put C in. All right, so that's the basic structure now we've created here. I'm gonna ask something. I can't remember what. Oh yeah, just that the inputs and output specifiers here that we use these to say like you'd expect, right? The inputs and outputs of this module. Not every wire, as we'll see, is going to be an input or an output. Some wires are going to be internal. But if we want to be able to connect 2 modules together, or if we want to be able to put external pins, connect external pins to these modules, they have to be specified as an input or an output. So that's what those specifiers are doing. All right. So inside here, I'm not gonna do a whole lot. I'm gonna let you guys do most of this. Write the logic here. And I will say that you should use functional. It's going to be a lot easier for you if you use functional over structural. In general, if your end goal is synthesis, I would say always use structural or behavioral. Never, sorry, not structural. Always use functional or behavioral, never structural. Structural is only good if you already have a circuit and you want to model exactly what that circuit is doing. Great. So I'm going to let you do this part. Reminder again, the logic you need for this part can be found right here. That is it. All right. So now let's go on to our 4-bit adder. Let me minimize this. I don't think I need to come back here. Let's go to our 4-bit adder. And same story, we need to create a module. And we want a module without parameters. All right. Here we go. So the module name here is going to correspond to my file name, which is 4-bit adder. Okay, and for ports here, this is our ripple carry adder. So this is going to be our 4 adders daisy chained together. So what should I put in my ports to create that? Like what should my inputs and outputs be? Okay, so a 4-bit input. So like here,
1-bit inputs.
4 1-bit inputs. So if I did like
There were like 1 4-bit inputs.
dot x dot y like that, or sorry, not without the parentheses, but is that what you're saying? So like x y.
I'm not sure. I don't think it was. Okay, yeah. Input wire X. Input wire Y.
So this wouldn't work. Yeah, exactly. Because these are just 1 bit each. So
The brackets with the colon.
yeah, it's the vector notation. So I want to look real quick, if we can, at an actual data sheet for an adder. Untile these windows for a second. So if we look at an actual data sheet for this adder here, then we have all these pins, right? And all these pins, if we look at them, they correspond to like A1, A2, A3, A4, B1, B2, B3, B4, etc. And then we have our sums here, which are our outputs and a carryout. So we think about what we're doing, we're actually designing something like this. So at the end of the day, this is what we want. Is you could think of it just like this, like a die with pins coming out of it that you would connect. In the last lab, we specified each of these pins individually as A0, A1, A2, A3, A4, etc. And I told you a bit that you could use vector notation, but I think it confused some of you, so I'm just going to go and quickly demonstrate what we're going to do. So, as was said before, we need something like this. This is our vector notation, and it always goes left to right when we do this, high number, low number. So what that means is that index 3 is going to be at the left side of this vector, whereas index 0 is going to be at the far right side. Yeah. Well, again, significance is in the eye of the beholder. But if you think of the most significant bit as being on the right side, then yes. If you think of it as being on the left side, because it can go either way, right? It's all about what you decide is significant, but we need to know how we're indexing into this array. So significance is a choice that we can make, but whichever way we decide, big endian or little endian, we still need to know how to get to the left or how to get to the right. And the general way that we do that is big number on the left, little number on the right. Does that make sense to everybody?
So if you were indexing the first bit of X.
Yes, if I was coming down here.
X3?
Well, what do we mean by the first bit?
From left to right.
Okay, if you're indexing the farthest left bit, then 3, yes. So if you're accessing this in C style or Java or other languages that you're used to, then it's backwards. We do it this way because when we're doing arithmetic, we always go right to left. The 0 place is on the 0, the 1 place is the next one, and so on. So that's why this is the standard, is because that's how you handle arithmetic. Yeah.
So just to make sure, the least significant bit is X0 or X3?
To be clear, significance is all about what you define your protocol to be. All we're saying here is that the third index, the largest index, is at the left of the array, and the smallest index is at the right of the array. But as far as significance, that's all about your protocol. This says, left or right, that's up to you to decide. But from a hardware perspective, we need to know if we need to grab it from the left because it's big endian, then do we index it 3 or 0? If we need to grab it from the right because it's little endian, do we grab it from 3 or 0? That's what we need to know. And that's what this is saying.
I don't understand why CN is 4 bits.
CN should not be 4 bits. I haven't finished this yet.
Oh,
Yeah.
okay.
Yeah, so we have an input wire 3 0, an input wire 3 0 here. Not 3 0 0, 3 0 0. We just have a regular input wire CN. And then we're going to have our outputs. An output, what size for our carryout? Or carryout? Yeah, a 1-bit carryout. And our output wire 30S. Okay, cool. So we don't actually need this guy. CN.
That's 0.
Yeah, so for the output, for the full 4 module, we don't know that it's 0. For the full chip that we're building, we don't want to be able to arbitrarily pass in a 5th bit, because where does it go in our chain of adders if our topmost, if our encasing IC has a carry-in? Where do we pipe that carry-in to? At which stage, right? Does that make sense?
Yeah.
So if we were to pull up this guy again, here, so this is what we're building. If we had a carry-in here, where would we put it? In which place? At which stage? Where would it go? Would it go at the final stage? Would it go at the first stage? We don't know. It's not well defined. In general, it just doesn't make sense to put a carry-in into our n-bit adder. So carry-in should only go in our single-bit adders that we're going to chain together.
Okay. The full ladders.
Yeah. So we'll go ahead and get rid of this one. We don't need it. Cool. All right. So, does anyone want to help me now figure out? So we've got this 4-bit adder definition here. What's the next step? What do we have to do to start chaining these guys together? What's that? Not a loop. A loop can only be used in a test bench. Yeah.
Use the adder file we have.
Uh-huh. So I'm going to write this, you said?
Yeah.
Okay. So like that. And then what?
And then we need to input into the adder. Well, we can start at x0 or x3. It doesn't matter, right?
It's up to you, I guess, to decide how you want to do it. I typically would start at x0 because when we're doing arithmetic, we're going to go from right to left. But I mean, we could say this is x3 or we could say this is the 3rd bit or the 0 bit. It doesn't matter what order we instantiate them in.
Let's do x0 then.
Okay, so you want to call this one
0th bit or something.
adder 0 maybe?
Yeah.
Okay, so just like that. And then, now what?
x0.
So, x0 like that?
Oh, we just have x, so we got x.
Right. Yeah, so we just have x.
In our adder,
And then what goes in here?
x0.
X0. Right. So to be clear, what we're talking about, the reason why this is outside here is x and not x0 is because in our adder file, we just defined it to be called x.
So This is just a hypothetical for understanding verilog. If X
Sure.
was like a 2-bit, so like X1, 0 there.
Uh-huh. So if this
How
was...
would you assign that in our 4-bit adder? Would you do dot X square bracket 0 parentheses X square bracket 0?
No. Buses have to be assigned all at once.
Okay.
Especially for inputs and outputs. There are some exceptions, but for inputs and outputs, a bus has to be assigned all at once. So if we wanted to say that X was a 2-bit adder, we would need to pass in a 2-bit input to X, which we just say like wire 1:0 X, like that, and then we could pass like that. So when we're doing buses, we have to define the entire bus.
Okay.
Does that make sense?
Yeah.
Does that answer the question for you?
Yeah, it does.
Great. Yeah, because otherwise it doesn't make sense from a hardware perspective to have certain pins set and other pins not set. In like if we're referring to this whole thing as one bus, then some wires have bits and some wires don't. Like, I mean, we can have 1s and 0s, but they're defined to be 1s and 0s. When we don't specify, it would be an undefined state.
Thank you. That was confusing myself.
Yeah, not a problem. So coming back to here for a minute, we'll set this back to X. And back to here, we have our adder. So dot X, we're going to give X, not X, but X0, like that. Just like that. All right, and then dot Y. Same story, right? And so on. So we'll do dot CIN. Now this one's a little tricky because we don't have a wire or anything right now for CIN. So what can we do?
Put in 0.
We could-
Go to 0.
We could put in 0 like this. You'll get a warning, and that's bad habit anyways. It will work, but it's not a good thing to do. No, we can pass in a constant. The idea to pass in a constant is right. The reason why this is a problem is because if we don't specify, then Verilog will assume 32 bits. And what will happen if we pass a 32-bit bus into a single-bit wire, it will just take the rightmost bit and use that and throw the rest away.
Can you do like, in that case, can you do like 1 apostrophe 0?
Exactly, so that's what we would do. This is how we would specify a constant in Verilog, and this is the reason why we specify it that way. So in general, I'm going to remind everyone that the constant here, syntax, is going to be number of bits, so say bits, apostrophe, and then the base, and then the number, the constant number that we want to represent. So, for example, if I wanted to represent the number 15 in 4 bits, there are 2 ways, well, there's more than 2 ways, but what are 2 ways I could do it using this syntax? I want to make sure you guys understand. Yeah, so I could do it binary and decimal. How would I do it in each of those formats? It's 4 ones. That's why I chose it. Yeah, you're good. And then that's binary. So in binary, because it's base 2, we have to specify every bit. And then so 4 apostrophe D. Yep, no. So 2. So remember that this is the number of bits that we're going to use to represent this. When it goes to hardware, it's all going to be binary.
Oh, okay,
4 apostrophe D,
What is it, decimal?
6 or 15. D is for decimal. Now, what that means, right, is we want to represent this number in this many bits. What the base specifier tells us is how Verilog should think about this number. Is this number hex? Is it a decimal? Is it a binary number? What is it?
So do we have to do 1 apostrophe 0?
You just do 1 apostrophe B 0 because it's a single bit.
Oh,
If you wanted to do 3 zeros, you'd have to do 3 apostrophe B 0 0 0, for example.
Maybe I missed this, but do you have a 4 apostrophe D15?
I do.
So did he ask if it should be 0015
Uh,
or should that be like 2 apostrophe D15?
Yeah, so I see what you're saying. The reason why it's only 4 apostrophe D15 is because this number doesn't say how many, this number has no bearing on this one. So this number doesn't say how many digits are we going to use to represent this number. It says when we go to synthesize this, how many bits are we going to assume are being used to represent this number. So in a sense, we're creating a constant bus here.
Okay.
So if we have 4, oh yeah, go ahead.
oh well, I have a question for you.
Okay, so if I have 4 tick D, then I'm going to create a constant bus of 4 bits, and that D tells Verilog what this number on the right, what the base is.
So if we did like 4 tick D30, that's more than just 4 bits. So
Right.
we would have some error there.
You'd have an error there, because it would say I can't represent that in 4 bits. It would either be an error, or it would be a compiler warning saying it truncated the bits.
So 15 is the max we can do
For 4 bits. Exactly. Which is why I chose 15.
Okay.
Yeah, so if I had chosen like 20 or something, that would, whether it would crash the compiler, whether it would stop compiling, I don't know. But it would be almost certainly an error on your part. That's probably not what you meant to do.
Okay.
Yes, question.
Can you do hexadecimal?
Yes. It's either, I think it's H. It's H or X. You can look it up. All right. So, Cn is 1 tick B0, which is again just the binary bit 0. And then we go to Cout, which is another one where we got to think about what are we going to do here. We need a wire to hold Cout. So we're going to create an internal wire. That's right. So here, we're going to say wire Cout1 and put in Cout1 here. Now, just a little pop quiz. What's the difference between this wire and this wire? They're both Couts. What's the difference?
That was in the outside world. It's being specified somewhere else, right?
It's not being specified somewhere else. It's going to the outside world
Oh, it's in the
because it's an output. But you got the right idea. It's if it's an output or an input, it means it's accessible inside another module or on the board.
This wire Cout1 you can only access in this file, in this module.
Exactly. Yeah, kind of like a private variable. But don't get confused and think it's really a private variable, because if I did something like this, assign Cout1 equals 0, and then later I tried to do something like this, that's an error. Look. Right, because wires have to be constant.
So it would have to be a reg, right?
It'd have to be a reg.
Do that.
Yeah. The reason why, again, physically, if a wire is connected to something, we can't just come in third party here and just inject something else
Right.
into it. And that's kind of the whole thing I'm trying to convey in this kind of lengthy, what could otherwise be rather short tutorial here, is that we are literally designing hardware. So we need to think about, when we're doing this, what is it that we're trying to design? How does it work in hardware? You get into that mindset, Verilog becomes a lot easier. Alright, so we've got our Cout, and just because I'm nitpicky, I want to call this Cout0 to go along with our adder 0. Okay, and then our output wire S, our dot S here, gets our 0th bit of S. And there you go. Okay, now you're obviously going to need more than just Cout0, and you we shouldn't assign cout at all. So this is from a previous demonstration I was talking about, but this right here would also cause an error because we're assigning cout something and then assigning cout something. Now we have two things trying to drive the same wire. You're going to get an error. So to go back to what it was originally, is say wire cout 0, cout 1, etc. Like that. And then you're just going to follow this pattern. What is the last cout going to go? So when we get to 4, where are we gonna put that cout?
Output wires.
Exactly. So that's going to be our output cout. And we get to the 4th one, then if it still carries, we'll get our cout. Are there any questions about this, about Lab1, about Verilog in general? Yeah.
Explain what you do on the last one again.
On the very last. So once we get to so we did some stuff, and then we get to adder 1 here. Where is our .cout going to go in this case? It's going to go to the outside cout. And that's all I was saying. The reason why is because this is our very last adder in the chain, and if it carries out, we need to know about that from our 4-bit adder, because that's what it means for the 4th bit to carry out. It means that the last adder in the chain carried out. Excellent. Everyone good? Alright guys, I am going to go ahead and turn off the projector. Just a reminder that for the first part, for the 1-bit adder, the information is right inside this file here, in the slides. It's down here.
Where are these slides?
They're in the Canvas files.
Okay.
But yeah, the equations you want are in these slides here from probably last week's lab, or last week's lecture, I mean. So, alrighty.